DDP, the Deep Dive Podcast.
Hey everyone, and welcome back to the Deep Dive. You know how this works. One of you sends us a fascinating research topic, and we kind of go down the rabbit hole together. Today we are diving into the Janus Cosmological Model by Jean-Pierre Petit. Trust me, this one's a real head trip.
It really challenges, the fundamental stuff, like what we think we know about the universe, and it offers a whole new way of looking at, everything.
Now, from what I've been reading, this Jean-Pierre Petit isn't just some, armchair theorist, right? He's a legit scientist, right?
Definitely. He's a French scientist, and he was at the CNRS, which is like their big national science center in France.
Okay, so we're talking about some serious scientific credentials here.
Oh, yeah. And what's really cool is how his model, this Janus model, is built on ideas from some of the biggest names in physics. You've got Einstein, of course.
Relativity and all that, right?
Exactly. Then you've got Sakharov, who had this idea of a twin universe.
Wait, like a mirror universe?
Yeah, kind of. And then there's Souriau, who did this work on something called dynamical group theory, which gets a little complex.
All right, so not exactly light reading, but this Petit guy, he took all these different ideas and kind of mashed them together into something new.
Yeah, and that's what makes this Janus model so fascinating. He's not just throwing out the old stuff, he's building on it, and it leads to some pretty radical ideas.
Like what? Give me an example.
Well, one of the big ones is the idea of negative mass. Your sources actually focus quite a bit on that.
Negative mass. Okay. See, that's where I need your help, because to me, that sounds like something straight out of science fiction.
I get that. It's not a very intuitive concept.
Not at all. So before we even get into this Janus model, can we back up a second? What is negative mass and why should we even care about it?
All right, let's start with the basics. We know that in our everyday experience, mass has gravity, right? It's what makes things fall to the ground.
Right. Apples falling from trees, all that.
Exactly. But what if there was a type of matter that had, negative gravity?
Okay, now that sounds like sci-fi. Negative gravity. So instead of pulling things in, it would push them away.
You got it. That's the basic idea behind negative mass.
And this Janus model is saying that this actually exists somewhere.
Well, it's more than just saying it exists. The Janus model actually tries to explain how negative mass could fit into our understanding of the universe without creating paradoxes.
Paradoxes.
Yeah. See, if you just introduce negative mass into our current model of physics, you run into some pretty serious problems. It's called the runaway motion paradox.
Runaway motion. All right, lay it on me.
So imagine you have a positive mass and a negative mass close to each other.
Okay, got it.
According to general relativity, positive masses attract everything, right? That's basic gravity.
So the negative mass would fall toward the positive one.
You'd think so. But here's the twist. Negative masses repel everything.
Whoa, hold on. They're attracting and repelling at the same time. What happens?
Chaos, essentially. The positive mass gets pushed away by the negative mass, even as the negative mass falls towards it.
So they're chasing each other.
Exactly. They end up stuck in this perpetual, accelerating chase.
That can't be right, can it?
It's not. It creates this runaway motion, like a perpetual motion machine, which we know is impossible.
Right. That violates the laws of physics.
Exactly. So that's why a lot of physicists have dismissed the idea of negative mass altogether. They're like, nope, can't work, moving on.
So how does the Janus model handle this? Because clearly, they're not just ignoring this runaway motion problem.
They're not. But for now, I think it's time to let our listeners catch their breath and digest all this incredible information.
Yeah, they probably need a moment to process all this. Until then, dear listener, ponder this. If the Janus model is correct, and negative mass does indeed exist, what does that tell us about the true nature of our universe? Is there more to reality than meets the eye? Join us in part 2 as we unravel more of these cosmic mysteries.
DDP, the Deep Dive Podcast.
Welcome back, folks. What's interesting about the Janus model is that it doesn't just try to fit negative mass into our existing framework. It proposes a completely new framework. It basically says, what if there's more to the universe than we can see?
More than we can see. What do you mean?
Okay. Imagine this. Instead of having positive mass and negative mass all mixed up together, what if they exist in separate sectors of space-time, like two sides of the same coin?
Oh, okay. So it's not that they're right next to each other, causing this crazy runaway effect. They're in their own separate domain.
Exactly. One governs the behavior of positive mass and energy, our familiar universe.
Makes sense.
The other governs negative mass and energy, which would exist in this other universe.
So not exactly parallel universes, more like two sides of the same coin.
Precisely. Each side with its own set of rules determined by these different metrics.
And these two sides, they interact somehow.
They can, gravitationally, but they're otherwise invisible to each other.
Wow, it's a lot to wrap your head around. Two universes interacting but invisible.
It's a mind-bending concept, but on a local scale, we can still use Newtonian physics as a simplification.
Newtonian physics, the good old stuff.
And even then, it gets pretty wild.
I'm ready for it. Hit me with the weirdness.
Okay, so masses with the same sign attract each other, business as usual.
Like we're used to here on Earth.
But get this, masses with opposite signs, they repel each other.
A positive mass and a negative mass would push each other away.
That's what the Janus model predicts.
That flips everything we know about gravity on its head. So the paradox is solved. But that still doesn't explain why we should even consider negative mass in the first place.
Right, and that brings us to another big mystery that the Janus model tries to solve. The mystery of missing antimatter. It's one of the biggest unsolved problems in cosmology. Why is there so much more matter than antimatter?
Right, like the Big Bang should have created equal amounts of both, right?
Exactly. So where did all the antimatter go?
Yeah, it's a real head-scratcher.
It's a puzzle that's been bugging physicists for decades.
And the Janus model says that, negative mass is somehow involved in this missing antimatter.
It does, but to get there, we need to go back to a fascinating idea by physicist Andrei Sakharov back in the 60s. He suggested that the Big Bang created two universes.
Two universes, whoa.
Each with an opposite arrow of time.
Like one where time runs backwards?
Exactly. One universe dominated by matter, the other by antimatter, in perfect balance.
Okay, so kind of like a cosmic symmetry, one universe mirroring the other. But how does this tie into negative mass?
Well, that's where the Janus model takes Sakharov's idea a step further. It suggests that there aren't just two universes, but also two types of antimatter.
Two types of antimatter. I thought antimatter was just antimatter.
That's what we thought, but the Janus model suggests that one type behaves like the antimatter we've observed in labs. It has positive mass and it annihilates with regular matter. But the other type is theorized to have negative mass and exists in this hypothetical twin universe.
Okay, so we've got two universes, two types of antimatter, and negative mass is somehow in the mix.
It's a lot to wrap your head around.
You could say that again. So is this all just theoretical, or does this model actually make predictions that we can test?
Well, the Janus model actually does a remarkable job of lining up with some of our current observations. We can talk more about that after the break.
DDP, the Deep Dive Podcast.
Welcome back to our deep dive into the Janus Cosmological Model.
Where we left off with two universes, two types of antimatter, and the very strange idea of negative mass.
And how it all might explain where all the antimatter went.
Right. Okay, so last time we kind of just accepted that negative mass might exist, but we never really talked about how it could exist. Like, what would even cause mass to be negative?
That's a great question. It's not enough to just say negative mass is out there somewhere. We need to understand why it might exist in the first place.
Exactly.
And that's where the Janus model gets really interesting. It draws on a connection between time reversal and energy inversion.
Time reversal and energy inversion. Okay, these are two big concepts.
They are, but they're actually connected.
But I'm still trying to wrap my head around how time reversal and negative mass are even connected.
Well, it comes down to symmetry in physics.
Symmetry, okay?
Think about a mirror image. It's reversed, but it still has a kind of symmetry with the original.
Okay, I get that.
So Dirac's antimatter, it's like flipping the charge, positive to negative.
Right, like the opposite of an electron.
Exactly. But Feynman's antimatter, it flips not just the charge, but time and energy, too.
We're flipping the direction of time. That sounds like some serious physics voodoo.
It is. But it turns out reversing time is mathematically the same as inverting energy and mass.
Whoa, so you reverse time and the mass becomes negative.
Exactly. And this comes from the work of a mathematician named Jean-Marie Souriau.
Souriau, okay.
He used this thing called symplectic geometry to show this connection.
Symplectic geometry? That sounds intense.
It's a branch of math, but basically it shows how time reversal and inverting energy and mass are linked.
So flipping time flips the signs of energy and mass.
Precisely.
Math is wild. It's like it unlocks these secret connections in the universe.
It really is.
Okay, so Feynman's antimatter has negative mass because of this time reversal, but how does that explain where all the antimatter went?
Reversing energy also means reversing mass. So in a universe with a reversed arrow of time, like the twin universe in the Janus model, we could expect to find negative mass.
Okay, I think I'm starting to see the logic here. It's like the math itself is saying that negative mass is possible, not just some random idea.
Right, it's not arbitrary. It emerges from these fundamental symmetries of the universe.
But how does all of this actually connect to what we observed? Does the Janus model actually explain what we see out there in the cosmos?
That's a crucial question, and it's where a lot of cosmological models fall short.
They sound good on paper, but they don't match up with reality.
Right, but the Janus model actually does a pretty remarkable job of explaining some of the biggest mysteries in cosmology.
Okay, like what?
Well, one of the big ones is the accelerating expansion of the universe.
Oh yeah, that's where dark energy comes in, right? That mysterious force pushing everything apart.
Exactly. But even though dark energy is a widely accepted idea, it's still a placeholder for something we don't fully understand.
It's like saying, we know the universe is expanding faster and faster, but we have no idea why, so let's call it dark energy.
That's a good way to put it. Now, here's what's really interesting. The Janus model offers a different explanation for this acceleration.
Okay, I'm listening.
Remember that repulsive force between the positive and negative mass sectors that we talked about earlier?
The one that keeps those masses from going crazy and creating a runaway motion paradox.
Precisely. Well, the Janus model suggests that this repulsive force could also be the driving force behind the accelerating expansion of the universe.
Whoa, so instead of this mysterious dark energy, the Janus model says it's just those two sectors of spacetime pushing each other away.
Exactly. It's a much simpler explanation, and it doesn't require inventing any new entities.
Elegant and efficient. I like it.
And it gets even better. The Janus model can actually account for the observed distribution of galaxies without resorting to another mysterious concept: dark matter.
Wait, are you telling me that negative mass could explain away dark matter too?
It could. While most models need dark matter to explain how galaxies behave, the Janus model can achieve the same results using just the interplay between positive and negative mass.
So all this missing mass in the universe, it's not actually missing, it's just the influence of negative mass from that other sector.
That's the idea. It's like we've been looking at the universe with one eye closed, and the Janus model gives us the other eye, revealing a much more complete picture.
I have to admit, this is pretty mind-blowing stuff. So the Janus model offers an explanation for the missing antimatter. It gets rid of that runaway motion paradox, and it even offers new explanations for dark energy and dark matter. Anything else this model can do?
Well, there is one more intriguing implication that we haven't touched on yet: the possibility of faster-than-light travel.
Now, that's something I definitely want to hear more about, but first we have to take a quick break, and we are back with the deep dive.
DDP, the Deep Dive Podcast.
Continuing our exploration of the Janus Cosmological Model.
Which has already taken us from missing antimatter to those mysterious concepts of dark energy and dark matter.
And now we're venturing into even more mind-blowing territory: the possibility of faster-than-light travel.
Yeah, that's what you teased right before the break, and I have to say I am very intrigued, but also a little skeptical. I mean, faster than light, that's like breaking the ultimate speed limit.
It definitely challenges our assumptions. But remember, we're talking about a model that already proposes twin universes and negative mass, so...
Right, at this point, anything is possible, but how could faster-than-light travel even work within this model? It still feels like we'd be breaking the laws of physics.
Well, not necessarily. The key lies in this concept of a variable speed of light.
Variable speed of light. Hold on, I think the speed of light was constant, like that was a fundamental law of the universe.
It is within our sector of the universe. But the Janus model proposes that the speed of light could actually be different in the negative mass sector.
So different rules for different sectors.
Exactly. Think of it like this. The speed limit on a highway might be 65 miles per hour, but on a racetrack, it could be much higher.
Okay, so in this negative mass sector, light could travel faster than the speed of light that we know, but how would we ever get there? And how would that even help us travel faster than light?
Those are the big questions, right? Well, Dr. Petit, the physicist behind the Janus model, has suggested that this difference in the speed of light could be exploited to our advantage.
How so?
Imagine creating a passage or a bridge between our positive mass sector and the negative mass sector.
Like a wormhole.
Exactly. If we could travel through this wormhole, we'd enter a region where the speed of light is different. And that means that traveling faster than the speed of light in that sector could allow us to cover vast distances in our own sector much faster.
So it's not about breaking the speed of light, but rather taking a shortcut through a region where the rules are different.
You got it. Of course, this is all very theoretical, but it's a possibility that emerges quite naturally from the framework of the Janus model.
I'm trying to wrap my head around it, but this is all based on the idea that the speed of light is variable. Is there any evidence for that?
There have been some interesting observations, especially in the study of distant quasars, that suggest the speed of light might have been different in the early universe.
Really? So our idea that the speed of light is this absolute constant, maybe that's not so set in stone after all.
It might need some revisions, and the Janus model is one way to accommodate these new findings.
Wow, this has been quite a journey. We've gone from trying to understand what negative mass even is to talking about wormholes and faster-than-light travel.
It's remarkable how the Janus model connects so many different ideas, isn't it?
It really is. I think it's safe to say that this deep dive has given our listeners plenty to think about. So to wrap things up, what's the one big takeaway you want people to remember about the Janus Cosmological Model?
I think the biggest takeaway is that our understanding of the universe is constantly evolving. New discoveries challenge our assumptions, and the Janus model is a perfect example of how we can use those challenges to push the boundaries of what we thought was possible.
Well said. And who knows, maybe one day we'll be taking those faster-than-light shortcuts to explore the cosmos firsthand.
I'd love to see that.
Me too. Thanks for joining us on this incredible exploration of the Janus Cosmological Model, and a huge thank you to our expert for guiding us through this mind-bending topic. We'll see you next time on The Deep Dive.